So my name is Gary Fredericks. I'm going to be talking about random number generators and how they relate to functional programs. I'm going to do that because I think it's interesting, and I could talk about it for its own sake, but also it's become relevant to me at work as a user and contributor to the TestCheck library. So I'm going to jump right in. So if you use the JVM, whether from Clojure or anywhere else, you're probably familiar with this class javautilrandom. This is the built-in random number generator. You can use it by passing it a seed to construct a new generator, and then you can ask for numbers, and it'll give you random-looking numbers, which is what you expected, so that's good. However, this is a stateful mutable object, and we hate that. But we know we can take imperative algorithms and translate them into functional algorithms. So how about we try to rewrite this in a pure functional immutable style in Clojure. All right, here we go. We're done. All we had to do was switch to the next slide, and the code was written. We have a create function, takes a seed, and it returns an immutable data structure. And then we have a next int function that'll take that data structure. This time it'll return a pair. There'll be the random number and also a new random number generator, which we need now that we're doing immutable things. That new random number generator helps us get more numbers if we need more than one. Otherwise, because it's immutable and it's a pure function, you just get the same number over and over again if you just use the same object. Okay, so let's see how this gets used. Starting on line 9, we can create a new random number generator with the seed. It looks like how it's printed on line 12. We can pass it to the next int function, and we'll get that pair. The left half of the pair is a random number. It's the same number from line 4. And then the right half is a new generator. If we call next int with the same argument, we get the exact same result. Same number, same new generator. And then if we call it with the new generator instead on line 17, we'll get a different number, different generator, and that number on line 18 happens to be the same number as on line 6. So looks like we've succeeded in reproducing the same algorithm, but in an immutable style. So that's good. Immutability is good, makes the program more robust. This seems like a clear win. However, these kinds of generators actually severely constrict what kind of programs you can write. The mutable and the immutable kind have the same drawbacks, but they manifest in different ways, and we will get into that. But for writing pure functional programs and composing them in a clean way, what we really need is called a splittable random number generator, and that's what this talk is going to be about. So this is our basic roadmap. We're going to, the talk is in 2 parts. We'll first talk about splittability, how it relates to program composition. We'll do some examples, talk about definitions. There'll be a longer example from real life with TestCheck. And then the second half of the talk will be about implementing splittable random number generators in Clojure. I should clarify that in case there's any doubt, all of this talk is going to be about seedable, purely deterministic random number generators. Anything that's non-deterministic, I'm pretending doesn't exist. And I'm also not addressing cryptographic randomness at all. My talk is not necessarily not related to that, but it's probably not related. Okay, so first half of the talk, splittability and composition. We're going to start with an example of a function that we're going to try to write from different approaches. So here's a function. It's called pair of lazy seeks. This is going to be a deterministic function that takes a seed, and it's supposed to return 2 lazy sequences of random numbers. The numbers should be different between the 2 sequences. They should look unrelated. They should be fully lazy, and they should be independently lazy. So there shouldn't be any underlying thing tying the 2 together where we might worry about memory leaks or that kind of thing. So there's a few different approaches that you could try with a mutable random number generator. We'll look at one of them. All of them are going to have some drawbacks. So I think the most naive thing you could do is write a function that takes a seed, constructs a javautilrandom object with that seed on line 3, and then use the repeatedly function. This is in EnclosureCore. It will take a function and return an infinite lazy sequence of values produced by calling that function over and over and over again. So in this case, our function simply calls next int on the closed over javautilrandom object. And we call repeatedly twice to get 2 sequences like we're supposed to. So let's see how this works. We can call it on line 1 with a seed, 42, destructure the return value into x's and y's, and then look at the first 4 numbers in each sequence. The numbers all look random. They're different between the 2 sequences, so from this angle it looks like we succeeded. But if we look at it from a different angle, in particular, starting on line 7, we call it the same way, same seed, same destructuring, and then just look at the first number in each sequence. The first number in x's is -1 billion, which was the first number in the x's sequence we saw on line 4. But the first number in the y's is 234 million, which is not the first number we saw in the y's originally. It's actually the second number from the x's. And if you're familiar with lazy sequences, this might not be surprising. We have essentially 2 functions that are both referring to the same stateful object. And because of the laziness, which random numbers appear in which sequence will depend on how you realize the 2 sequences. So the function that we've written is essentially not deterministic in a particular kind of way. So this is not an acceptable approach. But we can, surely if we write it in pure functional terms, it can't be non-deterministic, right? So we could just switch to our immutable random number generator and problems should go away. Here's a stab at that. We have a helper function up top that will take a single random number generator and return an infinite lazy sequence of random numbers. So the way you write this is on line 4, you call next int with your generator, destructure that pair that you get back into your random number x, your new random number generator, and then construct a list with x and a recursive call to random nums using the new random number generator. This works fine. You can actually generate an infinite list of random numbers this way. And then how do you write pair of lazy seeks? You take your seed, you presumably use it to construct a random number generator. That's the only thing you can do with it. You can pass that to random nums, but you need a second sequence. So you'll want to call random numbers again, and we don't have anything to call it with. You wouldn't want to call it with the same thing, you'd just get the same sequence. What we really want is the end state of the random number generator after we're done generating an infinite number of random numbers. And that kind of thing is not possible in our universe, so we're kind of stuck. There's just no way to write this. So with that, I'm going to move to this slide where we kind of try to clarify the space of concepts we're dealing with. The big realization I've had is that mutability and splittability are orthogonal concepts. So splittability is, well, first I should say what linear is. Both of the random number generators we've been looking at, I'm going to call linear because all they can do is generate a logical sequence of numbers. You can never kind of split that sequence if you need to do 2 things that are independent. And so a splittable generator augments that functionality with a split method or function. So in the top left, we have linear mutable. This is our javautilrandom. Lots of classic object-oriented random number generators fall in this category. The basic API is you can just ask for a number and you get another number. The immutable version in the lower left that we looked at already will have a function that returns a pair. So that's the only difference. Otherwise, you're still getting a sequence of numbers. And then the splittable versions will add a split function. So in the upper right, splittable and mutable, we simply add a method that will mutate the underlying object you call it on and then return a new random number generator that should be independent from the first one and generate different numbers. In the lower right, splittable and immutable, we're going to tweak the API a little bit. We no longer need to return a pair from next int because we have another way of getting more random number generators. So all we need is a randint function that returns a single random number, and then a split function that will take a generator and return 2 generators that should be independent. So it's worth pointing out that the change from mutable to immutable is a relatively cosmetic one. Given any mutable random number generator, there's some low-level coding process you can do. You can figure it out to turn it into an immutable one. But going from linear to splittable is not generally possible. There's no general mechanism for doing it. And as far as I know, most of the research into random number generators has not been oriented towards splittability, at least not the stuff that has leaked into popular programming languages. So if you go looking for random number generators that you can use in your programming language, if you're not in Haskell land, you're probably not going to be finding splittable ones. But Nevertheless, it's crucial for writing larger functional programs that can be composed in arbitrary ways, maybe have parallelism or laziness, that kind of thing, and still be fully deterministic. Okay, so let's look at how we might implement this with a splittable immutable random number generator. Actually, first, I want to clarify that in the top right corner, the splittable mutable one, I'm not going to be focusing on this much because immutability is a good thing. So while we're worrying about this stuff, we may as well aim for the bottom right. So most of this talk will be talking about immutable and splittable generators. Okay, so writing a splittable, or writing our pair of lazy seeks function with a splittable generator. On line, we have to change random nums first a little bit. On line 4, we're now going to call split on the generator first. To get 2 generators, we'll use one of them on line 5 to generate a number. And then we'll construct a list with the recursive call using the second generator. And then our pair of lazy seeks function is quite easy. On line 10, we create a new generator, and then we immediately split it into 2, and we'll call random nums twice with each of those 2 generators. So this works well. So now I'm going to transition into a more extended real-life example with TestCheck. So TestCheck is a property-based testing library. The way you use it is you will describe inputs possible valid inputs to your program by writing generators. You can use these generators to randomly generate lots and lots of different inputs. Then you also write properties that describe things that should be true about your program no matter what input you put in. And then the TestCheck framework can simply run tests by generating lots of random inputs and checking the properties against them. So this will be the basic example we work with. If you're not familiar with generators, this code up top will not make sense. But what it does is it generates a pair of what we'll call x's and x, where x's is a non-empty list of numbers, and x is one of the numbers in those lists. So you can see some sample tuples generated starting on line 11. These are all lists with numbers in them, and then next to it a number that we picked out of the list. Then we also have this dubious property. We don't have actually any code to test, but we can still write properties that say things about the things we've generated. So this property is called lists don't have duplicates. The way we write it is on line 2. We use the generator from the previous slide, and we destructure the generated value into x's and x. And then we simply count how many times does the number x appear in that list, and we assert it must be 1 on line 6. So lists don't have duplicates. Any item from the list must be there only once. Then we can run this property with TestCheck. We pass it to the quick check function, tell it to run the tests 100 times, and it gives us this failure data. Because it turns out that lists can have duplicates. In particular, on line 2, we have a list with 5 numbers, and the number 4 appears in it more than once, actually 3 times. The interesting thing about TestCheck is that when it finds a failure, it will then look for smaller and smaller failures. It will try different ways of shrinking the failing case it found and return the eventual smallest one that it could find by a shrinking process. And that one is on line 9. We see another pair. The list only has 2 elements, both of them 4s, and the number 4 next to it that appears in the list more than once. So we're going to dig into a little bit of how this shrinking process works. This is a photograph of what's called a shrink tree. The shrink tree is a massive, lazy data structure that gets generated with all your generated input, and it represents lots of different ways of trying to shrink input. And with this tree, the actual shrinking process is kind of dumb. It just does a greedy walk down the tree trying to find the smallest thing it can find that still fails. So the way that works in our particular case is at the root of the tree, we have our original failing input, that pair with 5 numbers. And then it will look at the children and see if it can find a child that also fails. All of the children are slightly smaller versions of the original. In this case, the first child fails, and so we immediately descend there and ignore the rest of the children. Then we look at that child's children. This time we have to go through 4 different test cases before we find one that fails. So then we descend there and ignore the rest of them. Again, we look at the children. The second child is failing, so we descend down there. This is our pair 4-4. And then at that point, we have to look through all of its children, and we notice none of them are failing, and so we stop at that point and return 4-4 as the smallest failing case we could find. So this works pretty well. I was using it, and for reasons I won't get into, a feature I wanted to add was the ability to stop the shrinking process in the middle of it with some information about where it had gotten to in the shrink tree and resume it later on some other machine. So for example, if our shrink got down to this third level and was at this node, assuming I had some path information about how we got there, I'd like to be able to start this up on another machine and have it resume from that point, which means I need to write code that will take the shrink tree and walk directly to that point in the tree, ignoring all of the passing nodes that the original process looked at. So I wrote this code, and a strange thing happened. It walked down the tree, got to this point, and it found a passing test. And actually, the value that was there in the original process was now different. The shrink tree was different in this new process, and this confused me greatly. But it turns out that the shrink tree was actually non-deterministic. This surprised me because I thought it was a deterministic process, had nothing to do with randomness, just try a few prescribed ways of shrinking things. There's no reason for it to be non-deterministic. But in fact, a complex enough generator actually uses randomness as it's shrinking. This is any generator that proceeds in at least two phases. So ours has two phases. We first generate the list of numbers, and then we use that list to select a random number from the list. So you can shrink that in two ways. You can select an earlier number from the list, or you can shrink the original list. And when you shrink the original list, the TestCheck will actually randomly choose another number from that new shrunken list. It does that to make sure that as it's shrinking, it always has a number that's in the list. You could imagine more optimal ways to do that, but that's a little tricky for TestCheck to figure out with the current API. So the shrink tree, the lazy tree, can require randomness as it's being realized. And the TestCheck was built with javautilrandom. So there's one javautilrandom object that all of this tree is depending on. And so the randomness that each node sees will actually depend on what order you walk the tree in. This wasn't a user-facing bug because TestCheck itself always walked the tree in the same way. But it prevented me from adding this feature and a few other features as well. So it seemed like, well, if we've got this non-determinism problem, we should probably just switch to an immutable random number generator. But the real problem, and I should say a linear immutable random number generator would not work here for the same reason it didn't work in our pair of lazy seeks function. And so what we really need is splittability. But because we value immutability, we decided that a good solution would be to do both things at once. And while we're mucking with this, let's switch to an immutable splittable random number generator. Because immutability will have a lot of other benefits for TestCheck as well. So this was the solution we decided. But there was then another problem, which is where do we get one of these? It's hard enough to find an immutable linear random number generator on the JVM, much less a splittable one. So it seemed like the only way forward was to implement one ourselves, which is a good segue into the second half of the talk. But wrapping up the first half first, we've talked about linear random number generators and how they relate to functional composition, how they constrain you to essentially linearize your entire program. And if you want to use laziness or parallelism, that might not be possible, or you just don't want to structure your code that way. So if you try to write general code with a linear generator, either you use a mutable one and your program might be non-deterministic, or you use an immutable one and you get stuck and can't write your code at all. So splittable random number generators solve this problem, but they are harder to find. And the TestCheck original implementation was fragile and difficult to add features to because it was using a linear generator. Okay. Implementations in Clojure. So we're going to look at this from 3 different angles. We're going to talk about some naive first attempts, and then some better research-backed attempts, and then talk about performance. So starting off, low-quality implementations. One thing you might want to try if you were approaching this is, can we take an existing linear generator and somehow adapt it to be splittable? So we can try this with javautilrandom for an example. This slide is trying to explain how javautilrandom algorithm works. When you call the constructor, you pass a seed in, and what it will do is take that seed and XOR it with a constant, and the return value there will be the state of the generator after the constructor finishes in blue. If you call nextInt, it will take that current state in blue, multiply it by a constant, and then add another constant, 11, and that will be the new state. And then the return value from the call to nextInt is taken from the top 32 bits of the 48-bit state. So just take those 8 hex values, convert them to decimal, that's the return value. If you call nextInt again, you just do the same 3 steps. Multiply, add, extract 32 bits. So that is javautilrandom. Any linear random number generator can be viewed as an infinite sequence of numbers. So if you're thinking abstractly, you might say, well, there's one way to convert a sequence into 2 sequences is by taking every other element and partitioning it into 2 sequences this way. And there's some obvious performance questions that jump out, like especially after you start splitting several times, what's that going to mean? But some algorithms will let you efficiently jump this way, and javautilrandom is one of them. All you have to do is tweak the constants that you're using, and you'll get a generator that performs just as fast, but logically is jumping some in amounts. So you can actually write this. But javautilrandom is not quite an infinite sequence of numbers because it has a finite state, so it's really a periodic sequence of numbers. The period length is exactly 2 to the 48th. The one I'm showing up here is 2 to the 5th because it fits on the slide better. But it's basically the same thing. So when you split a sequence like this, you end up with 2 sequences that are half the length. And if you split it again, you end up with 4 sequences that are 1/4 of the length. And if you do this a few more times, you end up in a very sad state for a random number generator to be in. The actual javautilrandom is a much longer period, 2 to the 48th, but it actually only takes 48 splits to get to this point. And for a general functional program, 48 splits is not unreasonable. Part of the reason this failed so drastically is because the period is a power of 2. So if this were odd, then it would work differently, but you would run into subtler problems. Another example of attempting this kind of thing, this is Haskell code. Don't look at it too hard, but this is the built-in random number generator in Haskell. It's been an immutable, ostensibly splittable generator for, I assume, decades. But right there on line 5, there's an interesting comment. This is the split function. It says there's no statistical foundation for this. So they tried something that seemed to work, and they put it in there because there, I assume, wasn't a lot of good research at the time. And there's been a lot of problems found with this. In particular, when you're using quick check, it's very easy to write simple generators that will never generate certain values because of how it uses split. So the lesson here is that writing a splittable algorithm, especially trying to bolt it onto a linear algorithm, can be very tricky. So let's talk about more professional ways to do it. There's a paper here on using cryptographic hashing to write a splittable generator. So we looked at this. The 2 concepts you need to understand how this works are the first one is a splitting tree. So this is just viewing the use of a splittable generator as a tree. So the code on the left corresponds to the tree on the right. We start with RNG1, created from the seed. That's the root of our tree. When we call split on it, we get 2 and 3, which are the child nodes. If we generate a number from RNG2, we'll call that x1. And in the tree, I've colored all the numbers that we generate blue. If you could take RNG3 and split that into 4 and 5, generate x2 from 4, etc. There's a lot of different shapes of trees you can have. So if you are using your splittable generator in a linear kind of way, by taking a number from the left half and then splitting the right half and continuing down that way, you'll end up with a shape like this. You might have a more balanced shape. Probably you'll have something more irregular in a real program. The other concept we need is a pseudorandom function. So this is just a function that's fully deterministic. When you give it an input, it returns something that looks unrelated but still deterministic. And in particular, with similar inputs, you'll still get unrelated looking outputs. This is the same idea behind a cryptographic hash function, which is actually something you might use in this case. So combining those together, looking at our splitting tree, we notice that each generator in the tree can be described uniquely by the path that we took to get there, the left and right steps. So the root of the tree has an empty path. When we go left, we add a 0. When we go right, we add a 1. And we can actually think about our splittable generator as simply being the pair of the seed and the path. And when we want to generate a number from a particular generator, we will simply pass both of those things to our random function. And if the random function is random enough, then this should work, because every call we make will have different inputs. And so by definition of the random function, they should have unrelated random looking outputs. So you might try this in Clojure with everybody's favorite hash function, SHA-1. You can do it with a def type. You have two fields, the seed and the path. If you want to generate a random number on line 6, you will combine the seed and the path together. Pass that to your SHA-1 function, convert the output if you need to. And then to split on line 9, you'll construct two new objects. They both get the same seed, and the path will have 0 or 1 added to it. And then we have a constructor at the bottom with the empty path. We wrote it. We assume it works good. How can we actually check if it works good? So testing the quality of random number generators is an extremely interesting topic. If you haven't read about it or thought about it, I encourage you to. It's a very kind of slippery concept, just trying to figure out what you're doing in the first place. First, you study statistics a lot, and then you get overwhelmed, and you start Googling, and you find out that there's whole test suites, open source test suites on the internet just for doing this exact thing. It's still useful to know some of the statistics as you're using this, so you can interpret the output better. We used a test suite called Die Harder because it was the easiest to set up. What it does is it will take a sequence of random numbers and run lots of different statistical tests on them. And for each test, it will output passed or weak or fail. But that brings up an interesting question, which is that Die Harder was oriented toward linear generators. It tests a linear sequence of numbers, but we have a splittable generator. How can we get a linear sequence of numbers that actually is meaningful for real-life use and will tell us something about the quality? I don't think there's any rigorous approaches to this. So what we did was just picked a few natural-seeming linearizations and tried all of them. So, for example, we have the right linear approach. I had this slide earlier where we just take numbers from the left and recurse down the right. You could do that the other way, left linear. You could also have an alternating linearization. You go left, right, etc. You might have a balanced linearization where everything's taken from the same level. Instead of 8, we used 18 quintillion so that we could pretend it was infinite. You might also combine the two approaches. So have the linear structure, but take batches of numbers at each step and just concatenate them together. And then you can do that down the other side as well. And finally, we had a more irregular structured tree based on the Fibonacci numbers. So we just took these 7 linearizations and tested all of them and hoped that that was meaningful for real-life use. So here are the Die Harder results. Die Harder will run 114 different tests. We're comparing here to javautilrandom, which did not perform very well. It's kind of a known thing that it's not very good quality. It only just does 2 pieces of arithmetic to generate a random number. It had 6 failures and a larger number of weak results. As I understand it, it's statistically inevitable that a test run will have several weak results, even for purely random numbers. So as far as I know, these results for SHA-1 are actually as good as we could expect. So it seems like we've succeeded in generating good quality random numbers. However, SHA-1 takes, say, thousands, I believe, of arithmetic operations to compute, and we're running it every time we want to generate a number. Meanwhile, javautilrandom uses 3 arithmetic operations, so there's performance concerns arise here. So let's now talk about other implementations that are hopefully a little less slow. The first thing you could try is use the previous algorithm but with a less slow hash function. So there are other cryptographic hash functions you could try that might be better. The original paper actually used a hash function based on 3 fish because they said it was more amenable to the way they were using it performance-wise. We also tried weaker non-cryptographic hash functions, so you have to have a little more worry about quality, do more testing, but it might still be good enough. But then there's also this class on the JVM called Splittable Random, of all things. This was added in Java 8, along with a lot of their streaming stuff. So this is a mutable splittable random number generator, which wasn't something I had even thought about until I saw this class. But it's you have the classic next long function, returns a long, and then you have a split function, mutates the underlying generator, and returns you a new independent generator. So we said that going from mutable to immutable is relatively cosmetic, so we should be able to do it here. So I'm going to try to describe this algorithm and then show how we can translate it to Clojure. So the algorithm's based on two what's called mixing functions, which are basically just random functions. The input size in this case is a 64-bit long. Again, I'm using a 5-bit number because it fits on the slide. But the function represented here, we have the inputs in the inner circle and the outputs in the outer circle. When you construct a splittable random object, you give it a seed, and that seed is simply set to be the initial state of the random number generator. So it's a trivial constructor. If you pass 24 to the constructor, the initial state will be 24. Then when you want to generate numbers, if you ask for a number, it's going to add a special number called gamma to the state, in this case 11. So 24 plus 11 gets us to 3. We pass 3 through the mixing function, and the output is 12. That's our actual output from the next long function. If we want another number, we're going to add gamma to the state again, go to 14, and then output 29. So we end up bouncing around the circle in a star-like fashion. Because gamma is an odd number, we'll end up hitting everything in the circle before we eventually repeat, which again is 18 quintillion numbers. So the period there will be 18 quintillion. Probably had something else to say, but I forget. Oh, and yeah, because the function we're using is a random function, then the outputs ought to look unrelated, even though the state transition is so simple. For splitting, though, this is the interesting part. If you want to split the random number generator, say we construct it with the seed 24, and we immediately call split. That means our initial state was 24, and then we're gonna add gamma twice to get 2 new states, and we're gonna use both of them to construct the new generator. The first one, we add 11, we get to 3, then we run it through our original mixing function to get 12, and that will be the initial state of the new random number generator. Then we'll update our state again, which takes us to 14, and this time we'll use a different mixing function called mix gamma. We'll pass 14 to that, outputs 25. Mix gamma is a special random function that will always return an odd number, because you want oddness so that you have a full period. And it also uses some other heuristics. So in this case, outputs 25, and that's going to be the gamma of the new random number generator. So the old one has its same gamma and its doubly updated state. The new one takes the state from the right and the gamma from the left. So you end up with 2 generators that have different gamma values, which means they're represented by different shaped stars. So even if they end up on the same state at some point, they'll immediately diverge and continue returning unrelated looking numbers. So we can write this in Clojure. This is all the code with the exception of the 2 mixing functions, which just do some low-level arithmetic. So we again have a def type with 2 fields. This time it's gamma and state. For a rand long on line 4, we add gamma to the state and pass it to the mixing function. And if we want to split, starting on line 6, we will add gamma to the state twice to get state 1 and state 2. We'll use state 1 with the original mixing function to get the new state for the new generator, and state 2 with the mix gamma function to get the new gamma for the new generator. We construct the new one on line 11 with new gamma and new state, and then the left half of the pair will still be a new object, but it represents the original object in the mutable version. So it will have the same gamma, and it will use the updated state, state 2. So this works pretty well. We can look at some crude benchmarks using criterion. This is testing how long does it take to generate 1 million numbers and XOR them all together. So remember, javautilrandom just does 3 pieces of arithmetic. These mixing functions each do, I think, on the order of 10 or 12 operations. So having a 3 to 4 times slowdown is not too surprising. This is obviously, I mean, slowdown's not the best thing, but the upside is that we get more quality random numbers, and we have an immutable algorithm we can use, which is beneficial in lots of other ways. We can also compare this to the SHA-1 implementation, which is severely slower. The die-harder results, here's both SHA-1 and the new generator on the bottom, are just as good, I believe. The actual number of weak results is the same as with SHA-1, so it looks as if we've got some significant speed up over the cryptographic version, but still retained quality. So this is what we ended up going with for TestCheck, and performance-wise, we weren't just concerned about how the random number generator performed. The real thing to test is how does a typical test suite perform under the new random number generator. So we'll look at that in a moment. But wrapping up this section, we talked about trying to write our own splittable random number generators from linear generators or other tactics, and it's not easy. But the professionals have done some work here, and there are a few different options we have. So that's good. Coming back to TestCheck, we added the splittable random algorithm that we just looked at. There's an alpha release right now, so you can try it out. Trying to measure the effect on actual test suites, we measured TestCheck's own test suite, which uses a lot of generators. So depending on what you measure exactly, the slowdown might be 10 to 20% or 10 to 15%. I've also heard various rumors of other people running it on their own test suites and seeing maybe up to 50% slowdown. So it's definitely something that we're considering. There might be more performance optimizations we can do, or say other faster options we can provide. But on the other hand, having made this change, and especially having now an immutable generator, there's lots of other things that we can add a lot easier to TestCheck. In particular, the first one, we can now easily parallelize the test runs without sacrificing determinism, which presumably will mean making them even faster than they were before we converted the random number generator. And there's also a lot of other things ways we can enhance it that are a lot easier now because of immutability. So all in all, it seems like a win. So this is my last slide. Summarizing what we've talked about, splittable random number generators are crucial for composing functional programs that rely on pseudorandomness and want to be deterministic. There are existing algorithms for this. Even on the JVM, there's a mutable version that we converted to an immutable version. And doing that made TestCheck a more robust library. So that's all I have. Thank you for your time.